So we're going to talk about putting large and small numbers in perspective with a pretty heavy emphasis on scientific notation, which probably the last time you dealt with that was maybe in a science class, maybe chemistry or something. But we'll get a good review of it if you don't remember. All right, so scientific notation is just a format in which a number is expressed as a number between 1 and 10. So the initial number has to be a single digit between 1 and 10. A single digit, I guess, whole number part. It can have a decimal, but it's a number between 1 and 10 multiplied by a power of 10. So 6,700,000,000 could be expressed as 6.7 between 1 and 10, and then we would just do times 10 to the ninth. Or another very, 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 very small number, which I'm not going to go through saying all those zeros, but that would be 2.0 times 10 to the negative 15th. Your calculator, just so you know, will generally express scientific notation instead of writing out the times 10 to the ninth, it'll have an E. So your calculator would express this number as 6.7 E9. And that E just means exponential 9, so times 10 to the ninth. Your calculator would express this number as 2.0 E negative 15. Does that make sense? Go ahead and give me a green check when you're good with that slide. So let's talk a little bit about how do we actually convert into and from scientific notation. So if I want to convert to scientific notation, step one, I'll move the decimal point to come after the first non-zero digit. In step two, for the power of 10, I'll use the number of places the decimal point moves. The power is positive if the decimal moves to the left and negative if the decimal moves to the right. And kind of the intuitive idea for me is if you're writing a very big number in scientific notation, you should have a positive exponent. If you're writing a very small number, meaning close to zero in scientific notation, you should have a negative exponent. So I'll give three examples here. So 3,042, technically there would be a decimal right there, right? Because it's 3,042.0. So I'm going to move the decimal place 1, 2, 3 spots to the left. So I'm going to have 3.042 times 10 to the power of 3 since I moved it 3 decimal places to the left. All right, that's a big number, so it has a positive exponent. This is a small number, meaning close to 0, so I'm going to expect it to have a negative exponent. But I'm going to use the same idea, move my decimal 1, 2, 3, 4 spaces. Now it's after the first non-zero digit, so I have 1.2 times 10 to the negative 4, since I moved it to the right, 4 spaces. All right, the last one, what I'm going to do first is actually multiply this out to be a standard number, and then I'll reconvert it back to scientific notation. The reason this isn't currently in scientific notation is because this is not between 1 and 10, right? So this is really 226 times 100. So 226, add 2 zeros. All right, so it's 22,600. And so again, I'll just put my decimal place at the end. Now I'm going to move it 1, 2, 3, 4 spaces to the right. So that's 2.26 times 10 to the positive 4th since I moved it to the right. All right, again, please participate by giving me a green check if you're good with that slide. If you have any questions, feel free to ask. Thank you. So this is maybe a review for most of you. Converting from scientific notation, the power of 10 indicates how many places to move the decimal point. You're going to move it to the right. If it's a positive power, you're going to move it to the left. If it's a negative power, again, if it's a negative power, it should be representing a small number, so you're going to expect it to be close to 0. If it's a positive number, it should be representing a big number away from 0. If moving the decimal creates any open places, then you fill those places with zeros. So if I'm doing 4.01 times 10 to the second, I would move that 1, 2 to the right, so that's 401. Versus 3.6 times 10 to the 6, I have to move the decimal 6 places. So 1, 2, 3, 4, 5, 6. Those open places get filled with zeros. All right, and this is 3,600,000. Okay, 5.7 times 10 to the negative third, that's a very small number, so we're going to be moving the decimal to the left. 1, 2, 3 spaces, so my decimal's here. Open spaces get filled with zeros, so it's 0.0057. Okay, so we know how to convert to scientific notation. We know how to convert from scientific notation. Now we're going to talk about how you multiply or divide and add or subtract numbers in scientific notation. Multiplication is commutative and associative, so it does not matter the order that I multiply things in, and I'm allowed to regroup them. So something like this, 6 times 10 to the second times 4 times 10 to the fifth, what I would do is just group the 6 and the 4, group the 10 to the second and the 10 to the fifth. All right, 6 times 4 is just 24. In the chat, what do we do with exponents when you have a product of powers? Little algebra review. How can I simplify 10 to the second times 10 to the fifth? What should I be doing with those exponents when I'm multiplying two terms that have the same base? Thanks, Naomi. Adam, that's what's up. So this is 24 times 10 to the 7th. Is this in scientific notation? Just give me a yes or a no. Is this in scientific notation right now? 24 times 10 to the 7th. No. Reason being, 24 is not a number between 1 and 10. So we can write 24 in scientific notation by moving the decimal. So that would be 2.4 times 10 to the first. And then I still have times 10 to the 7th. And then once again, I can just add the exponents there. So now 2.4 times 10 to the 8th. That is in scientific notation. Okay, same idea with dividing. I'm just going to worry about dividing the numbers in front, and then I'll deal with my powers of 10. And then I'll see, okay, if my answer is not in scientific notation, I'll do some adjustments like I did on that last one to make sure I put it in scientific notation. All right. 4.2 divided by 8.4. Well, 4.2 is exactly half of 8.4, so that's going to simplify to 0.5 times. All right, so you knew what to do with the product of powers. What do you do with a quotient of powers? What do you do with the exponents to simplify? Subtract them. Which order? Top minus bottom or bottom minus top? Top minus bottom. So it's going to be -2 minus -5, right? So it's actually -2 plus 5. All right, so that's 0.5 times 10 to the third. Again, this is not in scientific notation because 0.5 is not a number between 1 and 10. So what I want to do is move that decimal to the right once, so that 0.5 is actually 5 times 10 to the negative 1. And then I still have the times 10 to the third. Once again, to simplify, we're just going to add those. So that's 5 times 10 to the second. And that is in scientific notation. Okay, I went through a few slides there before checking in. Go ahead and give me a green check when you're all caught up with this slide, please. Adding and subtracting there's really no way around it. There's nothing you can do because we have exponents to simplify this without first just converting it to a number in standard form. So all you want to do is just rewrite your scientific notation in standard form. So 3 times 10 to the 6 would be 3. That's 3.0. 1, 2, 3, 4, 5, 6. Okay. So what is that? 3 million plus 5 times 10 squared is just 500. So I would get 3,500,000. And then if we wanted, we could convert that back to scientific notation, which would be 3.0005 times 10 to the 6th, because you're going to have to move that decimal back 6 places. So there's really no way around that. You just have to get it to be an ordinary number, then do the addition or subtraction, then convert it back to scientific notation if necessary. I'm going to skip those other two examples because it's the same idea. You're just multiplying everything out, then doing the addition or subtracting. All right? Okay, a little definition here. An order of magnitude estimate specifies a broad range of values, usually within 1 or 2 powers of 10, meaning within the 10,000s or in the millions, and science specifically refers to power of 10. So if you are 2 orders of magnitude away, you are at least 2 factors of 10 off with your estimate, which means you would be like at least a multiple of 100 off. All right, go ahead and get that definition written down. Give me a green check when you're done with. Did I? Okay. So in example 1, we want to know, is the total amount of ice cream spending in the United States measured in thousands of dollars, millions of dollars, or billions of dollars? And we'll say a reasonable guess that an average person has something like 50 servings of ice cream per year. All right, so if we operate under that assumption and do a little unit analysis, we can see that if we take 50 servings per year, and I don't know, this is where we're really roughly estimating, right? At $1 per serving. Yeah, sometimes it's going to cost more than that if you're going to your fancy boutique ice cream parlors, your Mary Coyles. You're going to it's going to cost more than that per serving. But if you buy just a gallon or a big tub from Costco, it's going to cost way less than $1 for one serving. You know, it costs like 15 cents or something like that. So if we average those out, about $1 per serving, and then population of the United States, right there, we're estimating to be 300 million, which is 3 times 10 to the 8th. All right. So if you multiply that all in your calculator, you're going to end up with, well, actually, let's not do this in our calculator. So what we actually have numerically, right, is we have the 50 times the 1 times the 3 times 10 to the 8th. All right, so 50 times 1 is just 50, times 3 is 150, times 10 to the 8th. Well, 150 is not in scientific notation, so if we want to convert it, I would move the decimal 1, 2 to the left, so that would be 1.5 times 10 to the 2nd times 10 to the 8th. Remember here, we just add our exponents, so that's going to get me my 1.5 times 10 to the 10th. And then my units are just going to be, right, servings cancel out, people cancel out, and I'm just left with units of dollars. So I have 1.5 times 10 to the 10th dollars per year. And if you actually multiply out 1.5 times 10 to the 10th, about $15 billion. So to guess within an order of magnitude, we'd guess that ice cream spending is probably in the billions of dollars, tens of billions of dollars. All right. So we're going to be using some of these measurements from table 3.1, and you're going to be asked to use them in your problem set as well. So just remember that this table 3.1 is in the slides, which are posted in the module. So if you need to access this, you can. And it just gives some energy comparisons where we're measuring energy in joules, right? So the energy released by the metabolism of one average candy bar is about 1 million joules, which is 1 times 10 to the 6th in scientific notation, versus the annual energy of the sun is 1 times 10 to the 34th power. So a 1 followed by 34 zeros, which is a very large number. All right, so what we're going to do is use that table to compare the U.S. population to the world population and the U.S. energy consumption to the world energy consumption. And then we're going to feel bad about ourselves as Americans. All right. So let's do that. So the U.S. population to the world population, we'll just go into our table here. Oh no, sorry. We're not going to go into our table. I'm going to give you the U.S. population for this one. So what we're going to use is, these were numbers from back in like 2012. So they've increased quite a bit. But the U.S. population back then, I'll just say as of 2012, was 3 times 10 to the 8th, which is 300 million people. And the world population in 2012, 7 times 10 to the 9th, okay, which is 7 billion at that point. And so if we simplify this just using our rules, I can just divide the numbers in front. So I'm just going to write that as 3/7. I can subtract the exponents, so that's times 10 to the negative 1. And 3/7 is going to be 0.043 approximately times 10 to the negative 1. Oh, I'm sorry. That already is after we adjust for that times 10 to the negative 1. So we get 0.043, which is about 4.3%. All right, so the U.S. represents 4.3% of the world's population. And now let's see how we do with energy consumption. So I'm going to do the same ratio, U.S. energy versus world energy. And that's what we're going to go back to our table for. So down here we have U.S. annual energy consumption, and we have world annual energy consumption. So the U.S. is 1 times 10 to the 20th, and the world is 5.3 times 10 to the 20th. And the same rules apply. So to simplify this, I would just divide the whole numbers, or the numbers in front rather, and divide the powers of 10. Powers of 10 are just going to divide out to 1. So now I'm just left with 1.0 divided by 5.3. Which, if we pop that into our calculator, is about 18.9%. So the U.S. makes up about 4.3% of the world's population, but uses about 18.9% of the energy annually in the world. So the U.S. consumes more energy than most of the world. All right. So we're going to look at just a couple more examples. So we're going to talk about looking at perspective through scaling. And scaling is dilating, meaning magnifying or shrinking, but keeping everything the same size relative to everything else. So that's what a map does, or a scale model that an architect might build of a building. And that means that all we have to do is multiply every measurement by some constant, which would be the scale factor. And we could get the true values of, our building, or of the distance from a map. All right, so we could say 1 centimeter equals 1 kilometer. On a map, they'll generally give you a visual scale like they do down here. So this distance is 1 kilometer. Or we could give it as a ratio. So 1 centimeter to 1 kilometer is a scale ratio of 1 to 100,000, right? Because there are 100,000 centimeters in a kilometer. All right. So we're going to use that to give some perspective. This is much better when we're in the classroom, because I could kind of use my room to give you perspective, but we're going to have to use our imaginations, and hopefully you have some sense of distance in meters. So the distance from the Earth to the Sun is about 150 million kilometers. The diameter of the Sun is about 1.4 million kilometers, and the equatorial diameter of the Earth is about 12,760 kilometers. Just remember, diameter the equatorial diameter of the Earth, what they're talking about there. Here's the Earth. Let me make it 3D for us. So the equatorial diameter is the distance across the Earth at the equator. And same idea for the sun, right? For the sun, though, we're just looking at the diameter in the middle. Okay. So we're going to use a 1 to 10 billion scale. And so that means this. I'm going to set it up like this. Our scaled Earth to sun distance. We're going to take the actual distance and scale it down by 10 billion. So 10 billion is 10 to the 10th power. Okay. All right, so we're going to do, the actual distance is 150 million kilometers. So we're going to write that in scientific notation. That would be 1.5 times 10 to the 8th kilometers. And I'm going to divide that down by 10 to the 10th. And so here I can just divide out the 10 to the 8th and 10 to the 10th. We'll subtract powers, so we'll get 1.5 times 10 to the negative 2 kilometers. Okay, so let's say we want to convert this to something that makes more sense, because thinking about what 0.015 kilometers is, it's a hard distance to figure out in your head. If we can just convert this to meters, that might be a little bit easier. So that's times, I want kilometers in the denominator. So there are what, 1,000 meters per kilometer. So when I multiply that out, kilometers canceled, I'm left with 10 meters. Sorry, 15 rather, 15 meters. All right, so if we scale the universe down by 10 billion, the distance between the Earth and the Sun is 15 meters. So now let's scale the Sun diameter. So scaled Sun diameter. So we're going to take that true Sun diameter, which was 1.4 million kilometers. So the true Sun diameter is 1.4 million kilometers. So 1.4 million is 1.4 times 10 to the 6th kilometers. And I'm going to scale it down the same way by dividing by 10 billion, which is 10 to the 10th. Let's just worry about dividing the powers of 10. So 6 minus 10 is negative 4. So what I end up with is 1.4, let's see, times 10 to the negative 4 kilometers. Let's go ahead and convert that to meters. Once again, there are 1,000 meters in a kilometer, but this I'm going to do this. So 1,000 meters is the same as 10 to the third. 10 to the third is 1,000. So there's 10 to the third meters per 1 kilometer. My kilometers cancel. Notice that here I just have 1.4 times 10 to the negative fourth times 10 to the third. 10 to the negative fourth times 10 to the third is 10 to the negative 1. And this is meters. And so if I move my decimal over, that's 0.14 meters. Again, 0.14 meters, you can probably have some idea, but maybe if we put it in centimeters, it'll resonate even more. So there are 100 centimeters in 1 meter. Cancel that. So that's 14 centimeters. Okay. So if we scale down the universe by 10 billion, the distance from the Earth to the Sun is 15 meters, which is like, I don't know, 3 car lengths, let's say, 4 car lengths, something like that. And then the size of the Sun, the diameter of the Sun is like 14 centimeters. So that's like a big beach ball, right? All right, what about the size of the Earth? Let's do that. So scaled Earth, we're going to do the same kind of calculations. I'm going to write it right here because I had bad space management. But we're going to take the true diameter of the Earth, which is 12,760. We're going to divide by, and that's kilometers, we're going to divide by 10 to the 10th. And so 12,760 in scientific notation is 1.276 times 10 to the 4th. All right, over 10 to the 10th. Divide these out, we get 1.276 times 10 to the negative 6 kilometers. All right, and then I'm actually going to convert this one. This one's so small that we're going to convert to millimeters. And I'm just going to tell you that there are 1 million millimeters, so 10 to the 6 millimeters in 1 kilometer. So kilometers cancels. 10 to the negative 6 times 10 to the 6, those are just going to divide each other out. And so my final answer is that the size of the Earth would be 1.276 millimeters. So basically, Earth is like the thickness that your thumbnail is in that setting. So Earth is the size of like a sprinkle, like a round sprinkle on a cookie. The Sun is like the size of a beach ball, and the distance between them would be like setting them on either side of 4 cars lined up, just to give you some perspective. So big. It's a big universe. All right, I think we're going to stop there. I just want to go over what you have to do before I see you next time, which is 2 weeks from now.